Hello everyone, I'm Eric Willett, Vice President of Technology and Development at Functional Products. Today I'm going to be sharing some of our work in troubleshooting and improving the water resistance of specialty H1 and bio-based greases. So for the work today, we're going to be looking at formulating calcium greases with varying H1 base oil blends and looking at how the polymer selection can affect the base oil blend and also how the base oil blend can affect the polymer selection in reverse. So we're going to look at three cases: medium solvency with white oil in group 3, low solvency with PAO, and high solvency is kind of an extreme example with bio-based vegetable greases. Then we'll talk about some high-level conclusions and kind of tie everything together. So grease formulating is quite an involved process. We make a lot of decisions up front about what types of base oils or thickeners we want to use, and then we kind of have to deal with some consequences of those selections down the road. For some problems that arise, like oxidative stability, we can treat them with antioxidants, or with extreme pressure, we can add EP additives. But when it comes to water, lack of water resistance is a pretty ingrained part of the structure and makeup of a grease that makes it very complicated to solve. And we find about two main cases where people are being driven to really kind of scramble to solve water resistance problems. And they tend to happen in specialty greases. So the first case that we see a lot of is people updating old GCLB formulations, which is a specification for wheel chassis bearings, to this new high-performance multi-use specification. One subcategory of the HPM is the water resistance category, and this includes a new test, which is the ASTM D4049, which is not seen in the standard HPM or the preceding, the GCLB types of specifications. So this is a new test that people have to tackle. So if you're unfamiliar with ASTM D4049, this is the water spray-off test where a thin layer of grease is applied to a plate. The plate is then sprayed with 40 psi warm water for 5 minutes, and the amount of grease which has been sprayed off the plate is measured and reported. So this is a great test for measuring the cohesion and the adhesion of grease, because you can actually see the grease getting pushed off the plate, which would be a cohesive failure, or the grease being lifted off especially the middle of the plate, which would be more of an adhesive failure. So we like this test because it's very rapid, where water washout is about a 1-hour test with quite an involved setup. Water spray-off is a really nice test for iterating and testing water resistance quickly. So you can solve problems in an afternoon where water washout may take a couple days. So the second category of cases is you have new markets opening up. You have bio-based, environmentally acceptable products. You have maybe some old formulators looking to investigate new markets, like incidental food contact. But if you see the production surveys every year for the grease market, you know most of the grease being made is lithium-based in petroleum oil. And when formulators try to break away from that kind of model, they end up in unfamiliar territory. And really what defines a specialty market, to me at least, is that you're working with a specialized list of components, or there's rules on what you can and can't use. So a lot of the knowledge is centralized in lithium or petroleum greases, and if you try to do something brand new, you might get stuck. So part of what this study is trying to do is expand the knowledge out there. The key way that we solve a lot of problems in grease formulation is with grease polymers. And we've talked a lot about grease polymers at lengths in training sessions and in prior conferences, so I won't get into the details today all that much. But the way you think of it is grease and a grease thickener is kind of like concrete and rebar. When we add polymers to a grease network, we heat up the grease network to about 80 to 100 degrees Celsius. We soften it up, open up some of those intramolecular bonds. We're able to incorporate polymer, and the polymer acts almost like rebar in a concrete structure. It provides mechanical support, long-range structure that the grease itself, because it's an arrangement of tiny individual salts, doesn't have. So for this study, we wanted to use a thickener system that was food grade, bio-based, and accessible to many different people. We didn't want to stick to some of the more proprietary and modern calcium sulfonates or aluminum complexes, but we do want to have something that's widely applicable. We thought that it was very interesting that these were, bio-based, food grade, edible, in some cases edible in other markets. So we also think it's quite timely in that the HPM, because it's removing certain tests or requirements like dropping point, that you will see more non-lithium greases in these high-performance applications. So we're using calcium stearate and calcium stearate acetate complex where it suits us. The way these calcium greases work is we're using calcium stearate mainly for the hydrocarbon base oils. This was the default, so we're using a fraction of a percent water with calcium stearate powders and dissolving them at 160 C in our base oil blend. For the bio-based work, we use a high oleic canola oil with a little extra antioxidant to preserve the base oil, but we have to remove the water. We can't use water because we're going to hydrolyze that ester structure. So instead we used calcium stearate acetate in place of the calcium stearate and water thickener. And this was effective. This worked. So the way this whole study began was originally with an industrial grease polymer, which is based on styrene. And we found that for some people that it was very effective in reducing or nearly eliminating water spray off. So going from 90% down to less than 10. In other cases, we had cut people with very poor or actually no effect on water spray off. And then we had a subset where they would see some kind of extra rubberiness or poor texture. So we wanted to capture under what conditions this is happening. There has to be something behind it. So we set out to model essentially 4 different types of formulators by creating 4 base oil blends. We have paraffinic and naphthenic for different types of formulators who prefer one or the other. We have this high performance PAO blend and a true incidental food contact white oil and PIB. So these are 4 different types of formulators who might see 4 different types of experiences with the styrene polymer. And we added it at about 1%, made the greases, and then checked the water spray off. So we ended up picking these base oils quite well. So if you compare water spray off versus the different base oil types, when we used no styrene polymer at all, we saw about 70% water spray off. But once we added 1% of the styrene polymer, we saw a slight improvement with the PAO, pretty decent improvement with the white oil, almost exceeding the HPM-WR specification. But it was these high solvency group 1 and naphthenic blends that really stood out in water spray off performance. And we actually reproduced for the naphthenic grease that rubbery texture that some people had run into. So I think we got really lucky with this data set and captured everything we wanted to see. And this base oil selectivity is not entirely unheard of. With styrene polymers or certain base oil thickeners, you might find some kind of base oil selectivity or performance changing with the base oil selection. So if you look at water resistance from high water spray off or poor water resistance to low water spray off or excellent water resistance versus base oil solvency, we kind of find this trend is that the PAOs have very limited effectiveness with the styrene polymer. But once we go to paraffinics where there's not this very low solvency condition, we start to get really good water spray off performance. And then once we start to go to the very high naphthenic solvency, we see water spray off get a little worse and we start to see that rubbery texture. So this kind of supports what people have seen in the past with styrene polymers. Okay, so thinking back, we're going to start trying to put some numbers on solvency, but let's think about solvency as an idea first. So we know from looking at the paraffinic versus the naphthenic oil that the key difference there is really the aromatic carbon is the biggest change, where the naphthenic oil had about 20% aromatic carbon and the paraffinic oil had about 4%. So they both had a lot of relatively high amounts of aromatics compared to PAO, but the naphthenic really stood out. The other thing is when we compare the white oil versus the PAO, these are both on the lower solvency side, but the naphthenes, the 30% in white oil versus none in a PAO, that kind of tells us that naphthenes are also important. So you see here these structures at the bottom where the red is an aromatic structure and the blue is a naphthene or kind of cyclohexane structure. This is what's driving solvency. So ironically, that styrene polymer is actually now HX1 listed. So we have this styrene polymer that likes a medium, a measured amount of solvency, but H1 base oils are really mostly known for being low solvency. But that's not really the case. I think a lot of people forget that H1 base stocks are actually quite diverse. We have white oils, group 3, some are H1. Alkylated naphthalenes would be a great addition to this project. And then we have things like PIBs, EPOs. We can replace those really low solvency MPAOs and build the base oil that we want to build. So we have the pieces. Now we need to figure out how to arrange them. We're going to use white oils for the naphthenic content. We're going to use alkylated naphthalene for the aromatic content. And the hypothesis is if we can reconstruct the base oil composition of that group 1 in bright stock or even that naphthenic oil, can we take a H1 base stock that is very low solvency and can we boost it up to that paraffinic group 1 type of level and get that really good water spray off performance? So we have to create a system, a numerical guide so that we can actually we know when we're taking the right steps forward. So like Hildebrand solubility or HLB, we're going to use percent aromatic carbon and percent naphthenic carbon to create a system of a kind of a compass. So we need to create a compass that's going to guide us on optimizing the base oil solvency in order to optimize the water spray off. So this is going to be our compass. We're not going to guess our way into a high performing base oil blend. So the way this starts is we're going to start off with a very simple equation. Solvency just equals the amount of aromatic carbon in the base oil blend. We're going to take our 4 formulations we've already made up and we're going to plot water spray off as a function of that solvency. Then we're going to apply a regression like you do in Excel and get an equation. We're going to use that regression to try and predict what formulations we should make next that will be closer to 10% water spray off. So we'll make up a couple formulations, test the water spray off, and review. Chances are our water spray off is actually going to be something like 40 to 70%, but based on our very primitive equation, it should have been 10. So there's something in there that we're not factoring. So we add an extra term to our very simple solvency equation to include some kind of hypothesis. So maybe we need to factor in the amount of MPAO or PIB, or maybe we know we need to include naphthenic carbon. So we'll do that step by step, recreate the equation, recreate the regression, and then refit everything. And we repeat this again and again, and every step of the way we're getting a little more accurate, a little more reliable in these equations. Okay, so after many, many iterations, what we find is that base oil solvency with H1 oils can be best represented with these 4 terms. So it is the percent aromatic carbon from things like alkylated naphthalene, the percent naphthenic carbon from things like white oils from group 3, and then we have to subtract out some base oil solvency if we're using synthetic oils like PAOs, PIBs, and then we can actually add back a little solvency if we're using viscosity modifiers that are based in light or low viscosity oils. So that carryover can actually improve solvency somewhat. So what we end up with is a plot of water spray off versus base oil solvency. The blue data points that you see are best fit by a third order S-shaped polynomial in Excel. But the red line is kind of manually put there, which I think best encompasses the behavior. So Between a base oil solvency of 0 and 6, we see almost no effect, which we've seen previously with the full PAO preliminary testing. As we increase base oil solvency with white oil, or group 3 and white oil and alkylated naphthalene, we see water spray off improvement. Our styrene polymer works better. If we add too much solvency, and really if we add too much of those viscosity modifiers, it's easy to add too much solvency, we see a loss of performance, as we've seen previously. So I think all of the behaviors that we expected to see are captured in the many iterations and plots that we've generated here. So if you're curious on what those best performing blends were in the plot I just showed you, they're reproduced here. They're using group 3 or white oil plus the alkylated naphthalene to generate the solvency of that group 1 and bright stock type of formulation. And then they're using a thickener like a olefin copolymer, a viscosity modifier, a PIB, or sometimes an MPAO to generate the ISO 150 viscosity. And what you want to target is a 10 on this base oil solvency equation, but a 9 to 11 does yield some pretty good results as well. Let's say we need to use PAO for some level of oxidative or thermal stability for a specific application. So we can't use the styrene polymer as we've established, even though it's high performance in a medium solvency case. We've shown that you need a certain level of solvency from rings or aromatics for it to function properly. So with these PAO types of structures here, PAO on the left, MPAOs on the right, we don't have that. Okay. So we can tune the polymer by taking out that styrene. We can make it actually less polar, so it will favor less polar base oils. So if we compare the styrene copolymer structure to white oil, alkylated naphthalene, even group 3s, you take out the cyclic ring structures and you're left with essentially PAOs. So we can do the same with the grease polymer. We take out the styrene content and we're essentially left with a very big PAO or a polyolefin copolymer. So these are going to look much like the styrene polymer and the more polar H1 oils. The polyolefin copolymer looks a lot like the PAOs. So when we go to use this polyolefin polymer, now that we've stripped out the styrene content, it is not as effective as the polystyrene polymer was. That 1% of polystyrene copolymer was highly effective, and that's why we went through all the trouble to optimize the base oil blends. But what we can do is, because this polyolefin polymer is a little more economical, we can just increase the treat rate. And what we find is that you increase the treat rate, here's the water spray off versus the amount of polymer we're using. If we just start at 1%, we pretty much haven't increased the base oil or the water spray off at all. But if we start to go to 2% or almost 3%, we can make pretty significant reductions in our water spray off. So if you're targeting the HPMWR specification, 1.75% is going to get you about a 40 water spray off. 2.5% is going to get you about a 20% water spray off if you really want to outperform in that category. We do find that the MPAO works best, and if you replace MPAO with something like a PIB, then the responsiveness of the polymer seems to lag or become a little worse. So the polyolefin looks more like an MPAO than it does a PIB. So we attribute to that kind of like dissolves like structure of those branched olefin polymers, versus the PIB has a lot more double methyl substitution, so it behaves a little more differently than a PAO. So our final category is probably the most exaggerated case of high solvency, which would be these environmentally acceptable vegetable oil-based greases. So they have, a number of technical challenges, but when we look at a bio-based vegetable oil grease formulation, the main thing that stands out is that low viscosity, that ISO 32, where your industrial greases are going to be mainly ISO 220, if not 460. So that's the big red flag. So we're going to tackle this problem as a matter of viscosity. So how do we get that ISO 32 viscosity up to something a bit more reasonable for our grease? That's the same as with any vegetable-based grease or lubricant project. So how high should that viscosity be, and how are we going to get there? So what we have for this are a range of bio-based viscosity modifiers that we've looked at that are high molecular weight polymers dispersed in bio-based oils, and you can use these to increase your viscosity. And in some cases, they are HX1. So we're not going to use polystyrene copolymers or olefin copolymers. We're going to use something a little different. So because our esters have very high polarity and some hydrogen bonding potential, we want to use things with high polarity as well. So things like double bonds where there's a lot of electron density, or where there's oxygen or nitrogen, there's a lot of polarity that we're adding to the base oil. And essentially what you want to do is you want to design the polymer, features of the polymer here, to look like the base oil you're trying to thicken. And this goes back about 10 years, some work we did at ELGI 2011. So you want to design a polymer that looks like the base oil if you want them to mesh properly. That's how you make a stable viscosity modifier for these exotic types of projects. So what we found was that there was a critical viscosity grade for achieving good water spray off. So we plot water spray off 100 to 0 versus oil phase viscosity. So just take the base oil, take the amount of viscosity modifier we used, and we're going to plot water spray off. We find a pretty gentle curve suggesting a good correlation between water spray off from ISO 32 down to about 3200 between water spray off and base oil viscosity. And we achieved this with two different viscosity modifiers, 50 SSI EAL eco-label listed bio VM, and also with a 30 SSI bio VM of a different chemistry. So the reproducibility on getting under 40% water spray off is pretty good. To achieve that, I would recommend targeting an ISO 1500 base oil viscosity. And you can deviate from that or develop from that as you need to, but starting at ISO 1500, it's going to give you at least a pass to start off your formulating project. Now, if you continue going on, let's say you want less than 10% water spray off, you can keep going up to about 3200, 4600. We kept going all the way up to 12,000, but didn't really eliminate water spray off at all. And this we did with our HX1 bio-based viscosity modifier. So you could scale this back and do the HX1 bio-viscosity modifier to ISO 1500 or 3200, as long as this plot here seems pretty flexible, because we're able to achieve good water spray off with two completely different polymers, and the correlation looks pretty reasonable. So to summarize, H1 base oils are actually extremely diverse. It's not just PAO or MPAO. And the same goes for the types of HX1 polymers or additives that you'd use to treat them. In the first case, we've looked at recreating the base oil solvency of a Group 1 in bright stock and creating it using H1 base oils. In the second case, we're using a polyolefin polymer to treat a polyalpha olefin base stock and improve the water spray off quite well. And in the third case, we've looked at quite an extreme example of treating vegetable oils which suffer from low base oil viscosity with bio-based viscosity modifiers and building up that ISO 32 to something a bit more industrial. So to put everything together, this is kind of the Rosetta Stone for all three cases together. Is polarity is a spectrum from low polarity to high polarity. At most solvent systems like Hildebrand, Hansen, HLB, this is kind of the critical point or critical part of the theories, is that there's an axis, there's a spectrum of low to high polarity. Your grease polymers are on the top. You want to pick grease polymers for your base oil below. So we used a polyolefin grease polymer for these very linear or slightly branched PAOs and PIBs. For the low or the medium solvency case, we used styrene grease polymers. So things that are a little more polar, they have this very interesting styrene functionality. So we're going to use that to fix our problems where we have ring structures. When we have naphthenes or aromatics, we match kind of the like versus like polymer versus oil structure. And then bio-based viscosity modifiers, we need to really increase the polarity and the solvency because esters have very high polarity, or even some PAGs. We didn't really talk about those, but they kind of, they're in the H1 kind of spectrum as well. So we want to use things with oxygen, things with double bonds. That will drive up the polarity, the electron density. That will allow the polymer to mesh well and thicken a base oil that looks very similar. So this is essentially the graphical conclusion to this whole study to put everything into perspective. So we covered a lot of ground today looking at different types of H1 based greases and how to address water resistance through the use of polymers. So we started off looking at this industrial styrene polymer, realizing it could become HX1, and then figuring out how we could build some low-cost, medium solvency H1 blends that would work well by reconstructing what you would find in a Group 1 or a Group 2 and Brightstock blend with all H1 components. Then the next step was we also looked at, okay, if you had to use PAO, you can't use the styrene polymer, what else could you use? Well, we removed the styrene functionality to create another HX1 polyolefin, and that worked quite well with the PAOs, but it wasn't as effective at the low 1% treat rate. And then last, with the vegetable greases, our method was looking at that low starting base oil viscosity, boosting it up to something more like an ISO 1500 to an ISO 3200. And then that's what we found was most effective in getting a more reasonable viscosity to what you'd expect in an industrial grease. So future work has two obvious points, would be to include water washout, which is still critical for the HPM specification at large, and the GCLB, and as well as looking at the options for H1 calcium sulfonate and aluminum complex. So these would be the other food grade thickeners. So thank you everyone for your attention today. We've covered a lot of ground, but I always hope that when we share this level of information that we're trying to do the most good for the widest number of formulators who might have questions about this category. So thank you again, and the technical paper will be available for more detailed reading. So thank you.